So I think one of the main reasons that you download Manim is to graph things because the graphs do look very beautiful. And the way we do that is we pretty much just change up the scene a little bit. So this is how you've been setting up scenes with the constructor in previous videos. And for graphs, what you're going to do is you're going to change it to type graph scene. So just your class is going to inherit the things from the graph scene. But then you also have to add in a config dictionary. So if you don't know what a dictionary is, it's pretty much just like it's a list of things where the indices are custom. So if you have no idea what I just said, just need to look up dictionaries, but it's different from arrays that we talked about last video, or array lists. These have custom. So for graphs, we want to add properties, let's say the y max. And don't worry about how I'm getting these numbers. I will pull up Desmos in a sec. So this is pretty much, I would say, the default template for a config dictionary. I did just copy and paste this, but I'll include this and relevant links in the description below. But this is pretty much just the basics of what you need for a graph. And if we go to the definition of a graph scene, you have all these different things, all these different properties you can change. And if you want to change it, you just want to include this in the config dictionary. So if I want to do any of these properties, you would add them just by a comma and then the name of it followed by the property. And you might ask, like, where I get these values from? Well, if we pull up a graph, this is the function I want to end up graphing, ln of x, sin of x, and I want to graph it from -2 to 14, and then that's going to be its domain, and it's ranged from -5 to 5. So this is just the grid by itself. So this grid is what this config is creating pretty much. So just the grid. And if we want to create the grid, first of all, in our construction, we need to do self.setupAxes, animate, and you can just, it sets up the axis of the graph, and you can choose whether or not to animate it. I'm just going to do true for now, but you can set it to false. I think by default it is false, so you can just not include that if you don't care. And in terms of the graph itself, what you want to do is just create a graph object like this and have it equal to self.getGraph. And normally, like when you graph a function, like say for ours is going to be ln of x, sin of x, but you're going to have to use something what's called a lambda expression. So first we need it first I want to import numpy as np so that we can do like the trig. But what you want to do is pretty much say lambda x and then the function. So mine is np.log, which is natural log in numpy, and then np.sin of x. We can also set the color of a graph if you would like to. I think by default it's white, but I just want my color to be yellow. Color palette is available in the description below if you just want to know. And then this also is an important property, xmin. So we want our xmin to be 0 and our xmax to be 14. And it's important we set our xmin to 0 because we have a natural log. So log of x is natural log in NumPy. And you can't take the natural log of 0. That's a discontinuity, which I will get to in a sec of how to deal with that. But we want our graph to only go from 0 to 14. And then to actually show the graph, you can do self.play as we've done before. We've also used show creation before, and then you just do graph. And then you set your runtime if you would like to change it other than 1 second. So I want to graph 5 seconds. And there's our graph. You might notice a small problem here that towards 0, our graph kind of forms a discontinuity, even though the Desmos graph does not form a discontinuity at 0. It just goes here. So what gives? Well, The reason for some weird shapes like this is because the program just needs to approximate it pretty much. So the way to get around having like asymptotes like this that you do not need, of course for functions like 1 over x, you would want your asymptote to be visible, but for functions like this, I don't really want it to be visible. So the way you get around this is pretty much just have the x min for the graph approach 0 pretty much. So I guess you could think of it as a limit. And since our x tick frequency is 1, let's get a better view. Since our x tick frequency is 1, and the weird shape starts at about 0.5, I'm just going to set the y min to 0.5 and see how that changes things. Much, much, much better. I mean, even though that we have a little fractured piece here, I think the overall graph still works fine. Before we do Riemann sums, I just want to show you how to graph the actual area under the curve really quickly, just in case if you don't want to go through this Riemann sums thing, you just want to get the actual area. So the way you would do that is you would create a variable called rex and call it self.getArea, really. Area of whatever graph you're doing. So for us, it's my graph. And then I want it to be from 2 to 8. So between these two x values. And then what I do is just do self.play show creation of rex. Because rex is an actual object, which you can do that. So you set your runtime, let's make it 3 seconds, and let's run this. Pretty neat, right? And now, the way we do Riemann sums is we have to set up a few things. So the first thing we have to do is we have to set up another dictionary. So you know how we set up the config dictionary? That would be for the grid of the axes that we did. We have to pretty much do a very similar thing for the Riemann sums themselves. So you could name this dictionary anything you want, but I'm just going to call it kwargs. That's just by convention. You could also call it Riemann vars or something like that, Riemann settings. And then here, what we need to do is we need to set the x min, just as we did with the getGraph method. So, and we want it to be 2. We want your x max to be 8. We also want to set our opacity. So fill_opacity. And let's just set this to 9. This just means it's 90% visible. If you were to set it to 1.0, that would be 100% visible. So that's the opacity property. And then I'm just going to set stroke_width to be 0.05. That's just the outlines of the rectangles. And with our Riemann settings, what we can do now is we need to identify how many times we want it to go from unapproximated to the actual area. So we're going to call this iterations equals 6. So what it's going to do is it's going to cycle 6 times between the approximated and the actual one. So you'll see what I mean. And now if we want to actually get a list of rectangles, we would want to do self.rectList, rect_list equals self.get Riemann rectangles list. And this just gets a list of rectangles from my graph, and then with a certain number of iterations. So the list just gives us all the rectangles in a list. So the first index would be a certain approximation, the next index would be, and it would cycle through the list. That's what the iterations does. And let's get our start color to be, I don't know, purple. And then our end color, let's make it, I guess, orange. Make it orange. Let's put this down here. Orange, and then we need to add in our arguments, so our dictionary here. So what you do is you do ** and Riemann settings. All right, and now once we have our list of various rectangles, we want to get a unapproximated version of them. We need to start from somewhere, right? So the way we do this is we create something called a flat rex. Again, this is also a name. You can name it whatever you want, but this would be self.get Riemann rectangles. Flat rex just means unapproximated version. So flat rex are just going to be their own. They're going to have their own function. So self.get underscore graph lam.x. We're just going to set this to 0. And then dx is going to be equal to 0.25. What this lambda x and dx mean, they're just a specific type of way to graph movement in Manim called like rate functions, which I'll get into another video. Don't worry about that too much just yet. Start color, we want it to be the inverse of the purple, and end color equals invert underscore color orange. And what it means is just we wanted to switch between the actual and the unapproximated version, and we want to have the rectangles do some kind of color change as well. So that's really what that means. And then we also want to include the Riemann setting. So star Riemann settings. All right, now we got our flat rex and our list of rectangles. Let's actually start graphing them. So first thing we need to do is we want to have our actual rectangles, and that's going to be the first object of our self.rectList. And it's going to be the first rectangles of that list. And then what we would do is we do self.transform underscore between underscore Riemann underscore rex. That's quite a mouthful. But this right here is the main method that transforms between the approximated and unapproximated. So we start using the flat rex, and then the rex, and then replace underscore manim object with target in scene equals true. Could have named it a shorter name, but and then runtime, let's say we want to make this 3 seconds. So it's going to graph the rectangles for 3 seconds. So let's run this. All right, these are our first set of rectangles. And that's how we that's how we draw our first rectangles. But if we want to keep approximating them and keep looping through them, there is this nested loop I found online by El Teorema de Beethoven. I'll link in the description below. But what this does is pretty much this loop right here is a nested for loop that like adjusts the colors as the rectangles change. And then this for loop actually, changes the rectangles to go from unapproximated to the actual area. I mean, the actual area for Manim is also an approximation, but don't worry about the technicalities of that. So yeah, we do self.transform between Riemann rex just as we did here, the exact same thing, except self.Riemann rect list, the previous list, and the next list. So it's going to go from the rect list goes from unapproximated to approximate. So it goes from least to greatest approximation. So that's why it gets the before rectangle and the after rectangles. But if we use these for loops and we actually graph it like so, boom, 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 and boom. It's pretty sweet, ain't it? And as we said before, we set purple to orange. So it's just gonna create a fade of colors. And then the blue here represents negative area. So it's gonna be the inverse. It just takes the opposite, not the inverse, but like the opposite of the color wheel. But yeah, that's how you do Riemann sums. And so the way you graph tangent lines are even easier than Riemann sums. They're pretty much just you're graphing an actual line on top of the graph. That's really all you're doing. So what you need to do is pretty much just find the equation of the tangent line. So I'm going to create a thing called tan line, not to be confused with tan lines you get at the beach, but tan line self.getGraph. We're going to use another lambda expression, x. And so this is going to be where our line equation is, and ultimately we do want to do self.play show creation of the tan line for, I guess, 1 time equals 2 seconds. And so in order to find this line, like you could go about it in different ways. Manim does have a derivative, like get derivative graph, but the graph just gets like gets that as another function. And so personally, I found the most like efficient way for me is just pull it up on Desmos. So this is the graph that we're working with, and on this menu here, you do have a tangent line menu. You go here, and you input your function here. And one thing you could also you probably have to do is also output the derivative, so output the slope. So if we want to graph the tangent line, let's say at I don't know 2.5. Let's say 2.5. We know that this graph right here is the line that we're going to be putting into Manim. So as you know, this is going to be 2.5 and 0.548. So what you do is 0.548 minus the derivative. So it's going to be 0.4946, 0.4946, and then you multiply this by x minus the x value, 2.5. So yeah, this pretty much is just the equation of tangent line you learned from Calc 1. That's really all it is. And then you can also do properties like color. I'm going to make this green. And then x min, I'm going to... this x min and x max for the tangent line is just going to be the length of the line itself, which is, yeah. So I'm going to make it from 1 to 4. So, you know, you can customize however long you want it to make, depending on, like, you know, the size of the graph. 1 to 4, bam. Let's run this program. Boom. Graphing parametric functions are similar to graphing the normal functions. So you pretty much define them into an object, except this time what we're going to do is we're going to do parametric function. Aha, as you see up here. There is parametric surface, but that will be for the 3D graphing video. Lambda t, because as you know, parametric functions are parameterized by a t function, which that's what lambda means. We're going to use mp.array. So yeah, an array. We're pretty much going to define our parameters in an array. So I want to graph a special function. Don't worry too much about the specificity of the things I'm putting in. This is just, I graphed this beforehand in Desmos, so that's where I got these x-mins and y-mins and y-maxes from. But yes, this is where you would put in your different parameters. So t plus 1. I would also like to square this. And then I'm also going to add a third parameter, which is 0. The 0 just means the z direction. And then you also have other features of the graph we would want to put in. So let's say color. Color, I'm just going to say magenta. And then this is going to be where your parameters are. So t-min, I'm going to say is -0.1. And then t-max is going to be 6.2. So the t values are going to go from this value to this value. Graph the coordinates of the x and y functions of the parameter. Of the parametric functions. So then we can just do self.play show creation of our curve, and I'm just going to say runtime equals 4 seconds. Vroom, 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 vroom. As you can see, it's like a little ribbon. It's a little ribbon right there. Yeah, I find that pretty cool. And if you want to graph polar functions, they do require an extra step, but really the idea behind a polar function is just have it equal to 1r, but Obviously in Manim there are no polar coordinates technically. I mean, you could, this whole polar grid, you could insert that in as an SVG image, but like in terms of like graph, you cannot graph this in Manim. What you need to do is transform it into a parametric equation. So you would say x equals r cosine theta, y equals r sine of theta, and then from there you can use other equations to convert this into its parametric form right here. So this is what we're going to be using in Manim. And so this is our function in a polar and parametric form. I've inputted into Manim because this took me a little bit, but yeah, you just input it in, use NumPy whenever you need to. And then I want it to go from 0 to 2 pi. Whoops, no, there is no 2 pi. You need to do pi. Pi is a enumerated type, so you can just do that. Play, show creation. Let's run this. This is good. Zoom, zoom, zoom. There we go. There is our boomerang. So yeah, that's pretty much all I wanted to show you for this video. Thank you for watching, and stay tuned for the next video for when we do 3D graphing. So yeah, we're getting into the fun stuff of Manim. So yeah, stay tuned.